All right. So now that we've talked about circuits, we're going to zoom in and look at some things that happen on the microscopic level within them. So first, we're going to formally define current in a circuit. And we define current as the way that positive charge carriers will move. And that should seem odd, because we just spent time talking about how it's the electrons that are moving, because electrons live in those valence shells and they're more easily removed versus those heavy nuclei that are tightly bound. So this is called a conventional current, this positive charge flow. This is purely a convention, and it does not affect any of our answers when we use this conventional current. It's just opposite the way of electron flow. And why do we do this if it's really the negatives that are moving and not the positives? Well, scientists guessed wrong. Because, of course, we discovered electricity before we knew things about molecular structure and the electron. So they just guessed that current would flow from plus to minus. So to maintain consistency, the conventional current is still used. So why it doesn't matter is it's essentially a double negative situation. Because if you flip the charge sign and the velocity sign, that's a double negative and it eventually cancels out. So when we talk about conventional currents, we picture the way a positive charge would move. So if positives are angry being clustered in the positive end of the battery, well, the positives would move this way. And this is called conventional currents. And when we say current, we mean this. Now, what's really happening is there's less negatives at the positive terminal and there's more negatives in the negative terminal. So the negatives would flow towards the positive end of the battery to correct that. Again, this is purely a convention. So it's not really the positives that move, and it doesn't affect our answers because of that double negative. And sometimes it's actually a lot easier to work with this conventional current because we never have to carry around negative signs. So just for some quick testing on our knowledge here, we want the direction of the net current, if any. So first we have a positive charge moving to the right. So let's say we have a positive charge carrier and it moves to the right. Well, of course, this is just going to be a rightward current because we said current is the direction of positive charge flow. And I have positive charge moving to the right. So of course, it's just going to be a rightward current. What about an electron? So we have an electron moving to the right. Well, if negatives are moving to the right, what does that mean? Well, if negatives are moving to the right, it must mean that there are positives over here and negatives over here, or something like that. So, if negatives are moving to the right, that must mean that a positive charge would want to move to the left, do the opposite. So, our conventional current is to the left. Of course, you could just know that electrons are going to flow the opposite in the opposite direction as conventional current, but there's your intuition as to why. Because if electrons are moving to the right, that must mean that there's more positives in that direction, so positives would be doing the opposite. A proton and electron each move to the right at the same speed. So if we have a proton moving at a speed v to the right, and we have an electron moving at a speed to the right, well, this would be zero current because there must not be any net direction of charge flow because they're canceling each other out perfectly. Here we have a proton moving to the right at speed 2v and an electron moving to the right at speed v. So we see in this case, the positive charge ends up winning, so it's a net positive charge flow to the right. So conventional current is to the right. These are more contrived scenarios. It's just practicing the direction of current. So when we talk about our microscopic description of current, we model a conductor as a sea of electrons, where they're not really attached to any atom in particular, and they're sort of a fluid that just exists between all the different atoms of the conductor. And these are always moving around between the atoms. And how it works is if there's no potential difference, these electrons are just flying around in all different directions. So this is a common misconception. Even when there's no current, electrons are definitely moving. It's just they're not tending to go anywhere. They're just flying around in this metal at all different directions. So there's not a current, because a current needs there to be a net direction. So notice that this electron's velocity is canceled by this one. This electron's velocity is canceled by this one. This electron's velocity is canceled by this one. So notice that since there's all these electrons moving in random directions, they cancel. So we call this a drift velocity if there's somehow a net direction that they're sort of creeping in. So if there is a potential difference, this means that there's going to be a push on these electrons. So the electrons will still have this sort of random velocity, but they're getting pushed on average towards one end. So if this becomes a positive end, regardless of where they're at, these electrons are going to feel a force. They're going to feel a force this way. So they're getting pushed this way. They're still random. A lot of them still cancel, but they're just tending to be drifting a certain way. So an analogy I heard, I'm going to guess it's from Veritasium. I forget where I saw it. You can think of these as sort of just sheep grazing in a field. So if there's nobody telling the sheep where to go, the sheep are just going to be wandering aimlessly in the field, eating grass, doing their thing. But we can think of a potential difference in this electric force as sort of a shepherd or a wolf, or we have a sheepdog that's barking at these sheep, trying to herd them towards the barn. So yeah, they're still going to be doing their thing. They're still going to be moving around, but they're getting barked at, so they're going to slowly make their way over. So it should be said that this drift velocity is really slow. It's really slow. People also think electrons move really fast because if you flip a switch, the light bulb turns on instantly. But that's really because it's the field, it's the electric field, and those effects happen at the speed of light, but that's a bit beyond our model. The actual drifting speed of this electron in the circuit is very small. It's on the order of millimeters per second. So it would take like an hour for an electron to make it all the way around a typical circuit. So it's really the field, this, which we'll talk about in a later unit, this electric field that propagates through the wire, and that's roughly the speed of light that happens. But we can actually calculate this sort of drift velocity. And it should make sense that the faster these charges are moving, the more current we get. And this is the relationship. And I should say, this is here for completeness only. And this is not actually on the AP Physics tests. We should know qualitatively that if you have a faster drift speed, you have more current or vice versa. And also, there's some things in here. I call this the I-nevA equation. I've also heard this called the Nevada equation. But what this says is that the current in a wire can be calculated by taking this value. This is the only weird one. This lowercase n is the free charges per volume. So this means the amount of charge in your volume that is free to move. E is, of course, the electron charge. V drift is how fast they're drifting, and the area. So it makes sense that the more charges you can pack in, and the faster they move, and the larger area, the more charge you can pump per second. So we'll verify this, but realize this is totally is a bit beyond the scope of the curriculum. This isn't even given to you on the formula sheet. So it says verify the above expression for current, starting from the definition that it is the total charge passing through a fixed area per unit time. So we're going to draw ourselves a wire. We're going to make it a circular cross section, although it totally does not matter. And we're just going to consider a part of it. So we're going to consider maybe this section of the wire. So it's going to have the same cross-sectional area, and it's going to have some length that we'll consider that we'll just call it X. So our definition of current says that current is defined as the amount of charge that passes through an area every second. So we can start just by finding the amount of charge. So what would be charge? Well, the total charge Q would be equal to the number of electrons that are free to move in the volume times the electron charge, or sorry, we'll do times volume, then times the electron charge. Right, because this tells me how densely the electrons are packed. So if I multiply the density by the size, I get the number of electrons, and then I just tack on the charge that each of them carries. So if we did this, electrons per volume, that's lowercase n. And now what's the volume? So this is the weird part of the derivation. So we're looking at what would be maybe this volume. Well, the volume of this would be the cross-sectional area times the length. So we'll pause there for a second. So we're saying the volume of this shape is going to be the cross-sectional area, so the base, times the distance x that we've extended it. So that's a formula we'll use a couple times in this class, that volume is equal to area times thickness if it's a uniform shape, or the same thing that area can be length times thickness. So that's Q. So now we can just plug into our formula that says current is equal to Q divided by time. Q is N times A times X divided by E divided by T. And notice we made this value of X up, so it better cancel or do something. So it will actually, because notice we can cleverly group this. So I'm just doing some reordering, just so we get the formula in the form that we want it. So I is equal to N times E times the quantity X divided by T times A. So what is that? X divided by T would be the rate at which charges move through a distance. So that is, of course, a speed, distance over time. So there we go. I nevA. Again, not totally in the scope of Physics C, but it's important to at least relate. Current depends on charge carrier speed. It's the speed that they're drifting. So remember that all the charge carriers are moving very fast in random directions, but they're very slowly creeping in some direction if there's a potential difference. And that's what creates the current, is that slow drift speed. Sometimes instead of talking about the total current in a wire, we'll look at its density as how it's packed in an area. Because this can change throughout different wire segments. You can imagine if I have like a larger pipe, you want to think about current as water, and then we have a smaller pipe, the current would be more densely packed if you have to shepherd those electrons into the smaller tube. You can think of it as fluids, which is pretty useful. So the current is I, so we go one letter further and make the current density J. So any sort of density, this is a useful fact that you might not have totally made the connection over. Density, the universal formula for density is equal to the amount of something divided by the size of something. So we can pick all these different densities, like mass over volume is the chemistry version. So notice here, our density is the amount of current per area. We can also define things like a volume charge density. We can define electron volume density, linear mass density. All these densities are something divided by a size. The most common type of density we'll see involves in the current density inside like a cylindrical wire. Most wires are cylindrical. So a wire has circular cross-section of radius A, and it carries a current I distributed uniformly throughout. And we want to find what the current density is. So this is our wire, and it says we have a uniform current per area. So we can say that J is defined as the current divided by the area, which is I divided by the area, pi little a squared. And notice it's really clear from this that it is showing a current and an area being divided, because that pi a squared is, of course, our circle area. So again, the area that we're actually talking about with density is the actual cross-section, so we don't have the full cross-section here. Now, in terms of the total current I, derive an expression for the total current enclosed at distances at most a over 2 from the wire center. So we know we have a current I in the whole thing. So we're actually asking how much current would be in this circle. Because we know it's not I, because the whole circle can transport I. So there's, of course, you could actually do it two different ways. I'll show maybe the more like precise way that you might pick, but this is a really nice ratio question. So if we rearrange, we know that J is defined as current per area. So that actually means that current is just equal to J times A. So we know that throughout the entire wire, J is constant. So I'm going to give that a multiplier of times 1. But then if I go to my area versus the original, I'm only going out to half the radius. And one thing, this is our first time of many seeing this in this class, area is a squared quantity with respect to distance. So if I half the radius, I 1/2 squared the area. So that actually means that my new current, so I'm going to say that my I, we'll call this I new. So my new current is just going to be 1/4 of the original. Now, if you didn't want to do this with ratios, you could plug and chug. I would advise against this. I really like thinking about this with ratios, and it's good physics practice to not just be plugging stuff in. But if we use the formula that I is equal to J times A, you could get our J from the previous part, I over pi A squared, times our area, which is pi times A over 2, quantity squared. Let me see, I gotta scoot it over a bit. And what is this? Well, we'd get I over pi A squared times pi A squared over 4, and oh look, how nice. Pi A squared goes away, and I'm left with exactly 1/4 of the current. As expected. So, of course, you can always do it like this. I'm a big fan of multipliers, so we're only going to do this with multipliers for part C. If a wire of the same current density was used, derive an expression in terms of A for the new radius needed to get triple the current. So we already came up with this equation that says I is equal to J times A. And what we want is triple the current. And it says same current density. So we want the same current density, but we also want triple the current. So notice that what we see here is, well, if I multiply 1 by something to get to 3, it's got to be 3. So we're actually given that area triples. But triple the area is not triple the radius, right? Because it's quadratic. So that's great. This is a great intermediate step, but we also know that area is equal to pi r squared. So if I'm tripling the area, I have to ask, what needs to get squared to become 3? Well, of course, this is just going to be question mark squared equals 3, so that's actually square root 3. So this says that in order to get triple the area, we need to root 3 our radius. So our new radius is root 3 times our original wire radius. That's tricky. Now, you could work it out again, right? You could totally do it like this. If you love this and just the plugging and chugging, absolutely do it. It will totally work. Because you would get 3i equals I over pi a squared times pi r squared, and you get r's root 3a. But I think this is a much more elegant way of doing it using multipliers. So our final circuit topic that we've kind of moved around last time was this idea of resistance. And there's not a great definition of resistance for now, but just think of the word. It's a component's tendency to restrict the flow of current. So if your resistance is high, you're not going to get a lot of current for the same battery. But at a microscopic level, we can think of resistance as how difficult or how much time does it take for the electrons to go between 2 points. So think about resistance as how long it will take, on average, the charge carriers to progress. So here we're going to try to derive the formula, or at least gain some intuition. So the first thing that could matter for a segment is its length. And we want to justify using collision theory each time. So which of these wires is going to have more resistance, A or B? Well, we're really asking what takes longer for electrons to, which is going to take longer. So we fixed the area of these segments and just made one of them longer. Well, of course, if you're trying to go down a hallway and you're just walking down a hallway, you got a longer hallway of the same size, it's going to take longer for a crowd of people to file out of the longer hallway. So wire B has greater resistance. Greater length yields more collision / travel time, so B has greater resistance. So think about it as all these people are trying to file out of an exit after maybe like a concert or a movie. Well, if there's a longer hallway, it's going to take them longer to get to the end. What about increasing the area? So let's say it's the same number of people that have to exit the movie theater. Wire C is kind of crowded, but wire D, the area is bigger. So if there's a bigger area, and the length being the same, the greater area should actually take less time to get through. Because you can imagine if your hallway's really constricted, the people are going to be bunched up together. It's going to be harder for them to actually make it through to the other side. So of course, wire D is going to take less time. So a smaller area makes collisions more frequent, so C has greater resistance. Right? Imagine if you have a really constricted hallway, you're going to be bunched up with those people. So it's going to take you longer to get out than if you're not bumping into people. You got all that free space to yourself. This is a new concept. It's called resistivity. This is a molecular property, but we can model this as roughly the amount of obstructions that the electrons would be hitting. So same length and area, except now there's just much more obstructions in wire F. So wire F is going to have more resistance because, of course, if there's more obstructions or things to bump into, if you're trying to file out of the hallway and there's just a bunch of poles in the middle of the hallway or a bunch of just obstacles, of course, it's going to take longer to get through the one with more obstacles. So let's zoom out here because it's going to have us construct a formula given that it's a linear dependence. And it depends on only these quantities and there's no constants in front. So we said, if you have more length, you should have more resistance because it's going to take you longer to get to the other side. If you have more area, it's going to take you less time to get to the other side because you're not going to be bumping into people as much. And if you increase the resistivity, which is the obstruction density, that's also going to take you longer to get to the other side because you're bumping into things more. So this means that, so let's do that. So as L increases, R increases. As A increases, R decreases. And as resistivity, rho, increases, R increases. So again, the relationship tells you if it's numerator or denominator. So if the relationship is the same between the quantities, it's numerator, because that would be multiplication. And if it's an opposite or inverse relationship, it goes on the denominator. So we can say resistance must depend linearly on resistivity, or sorry, it must have a numerator relationship with resistivity and length, and a denominator relationship with A. From this alone, you cannot argue that this is the formula. I had to tell you that it's a linear relationship. Like, notice I could have just created some weird exponents on this, and this would also be valid. But I actually am just telling you that this is linear. And also, there could be a magic constant in front, but we absorb all constants into this material property called the resistivity. Suppose a metal wire segment is heated to a high temperature. Indicate whether the resistance will increase, decrease, or remain the same. Justify your answer in terms of collision theory. So again, we said more frequent collisions means a higher resistance. So if we bump up the temperature, that's going to make these particles flying around faster, and they're just going to be hitting each other more often. Because yes, the particles are going to be moving faster, and you'd think they might be able to progress to the end a bit quicker, but we're really thinking about the frequency of collisions as resistance. So resistance will increase because particles speed up, so collisions become more frequent. Because really, we're saying that resistance is proportional to collisions, or collision frequency, we want to say. Because every time you collide, you get a bit more derailed. So we're going to say it's proportional to the collision rate. And again, this is totally an analogy to try to reason that this is the formula. All right, so now we got some new units. So resistance is given by this expression we came up with above. Resistance is measured in ohms. So that's actually not the worst ohm I could have drawn. We will come up with a more familiar way to express the ohm next time. But this is our resistance unit. Length is meters, area is meters squared. So to get everything to work out, resistivity is ohm meters. There's not a great way of interpreting this unit, but we should note that resistivity is a huge range. So for conductors, we can get resistivities of 10 to the minus 8 ohm meters, but for insulators, we can get like 10 to the 10th. So there's a huge range of these. So now we got another ratio question. A cylindrical resistor has resistance R1. Another resistor of the same shape and material is constructed with double the length and double the radius. This resistance is R2. Determine the ratio R2 over R1. So we're essentially asking how much more resistive or less resistive is R2 than R1. So usually with these ratio questions, you don't want to work it out. You actually want to just come up with a formula and do multipliers. But it is nice to just draw it out. So this is going to be like our first resistor. Has length L, and it has a radius R. But then our second resistor is going to have double the radius, but also double the length. So it's not obvious it's actually not obvious whether our resistance should increase or decrease just by looking at it. Because we have double the length, which means there's going to be more collisions, there's a longer hallway, you're not going to get out as quick. But also, there's double the radius. So your hallway is bigger, so people might not be colliding as frequent. So it could be anything. It could be larger for R2, it could be smaller, or it could be the same. So our formula for resistance, we're going to say that R1 is equal to rho times L divided by A. This is how I like to do ratio questions. I just write my original formula. So what would be R2? Well, we can find R2 using multipliers. A key part of this problem is it's the same material. So since it's the same material, resistivity stays the same. So resistivity is entirely determined by material. Copper is different than silver, which is different than plastic. So you can only change resistivity rho by changing the material. What about L? L is double for the new resistor. But so is area, or sorry, so is radius. So what does that do to area? Well, third time today. Area depends on radius squared. So my area gets multiplied by 2 squared. Double the radius, pi r squared. I have to square it. So what does this turn out to be? Well, this actually tells us R2 is equal to, we get a 2 on top, and we get a 4 on bottom. So we get 2/4, which is 1/2. And that's actually not what we want yet. We want R2 over R1. So R2 over R1 is just going to be 1/2. So not necessarily the most clear just by reading it, that this actually has half the resistance. Most common answer would be it does nothing, because you'd see, oh yeah, double the length, double the radius. They'd think area doubles, so it just cancels. But of course, radius actually means more because it's a quadratic. And now here's a weird one. I say this is a weird problem because there's a weird twist to it. A wire with circular cross-section has an initial resistance R. The wire is then stretched to triple its original length while keeping the volume constant. Derive an expression for the resistance of the new wire. So think about this as like a strip of Play-Doh. That's what it means by keeping the volume constant. It means there's only a set amount of the wire you have. So if we stretch the wire to triple its length, keeping it constant, so we're originally going to have something like this. We're stretching it to triple its original length. So, and there's going to be resistance R. Think about what that means. That would mean rolling out your Play-Doh, so it's 3 times as long. Well, if you roll out a strip of Play-Doh, it doesn't stay this area. It actually gets a lot skinnier. So the fact that volume remains constant actually means it doesn't just get longer, it also gets way skinnier. So that's why I say this is a weird problem, or there's a weird twist to it. It's actually a lot more realistic than some of the others, because you can't just create extra volume on this if you're stretching it. So it's going to do something to the area. And we actually have to use our old friend from the I nevA derivation, that what is volume? So volume, which is constant, is going to be the area of the resistor times its length. So given the fact that we know that the volume remains constant, right? That is forced. That is forced by the problem, that volume remains fixed. So if you actually stretch out the wire to 3 times its original length, you must have made its area 1/3 of its original value to compensate. So it's actually the area skinniness exactly counters the lengthening process. So this means that our new area is actually 1/3 of the original. And now it's just a multiplier problem. So our new resistance is just going to be rho L over A. length was tripled, area was thirded. So we get 1/3, we get 3 on top and 1/3 on the bottom. So 3 divided by 1/3 gives us 9 times the original resistance. And this time they're not partially canceling, they're actually working with each other, because a longer wire increases resistance, but so does a skinnier one. So this is actually a large increase because both effects are helping. Now we got our first ranking to do. So we have all these different resistors of given radius. So we're given that a radius of r, little r, corresponds to an area of big A. So this one, I half the radius. This time I double the area. This time I double the length. We want to rank the resistances and justify our ranking. So I always like to start with justify your ranking, because if we're ranking resistances, there's really only one formula we know. Resistance is resistivity times length divided by area. But also, I've noticed that I'm not actually given the area directly for some of these. Sometimes I'm actually given the radius. So I also should take note of the fact that area is equal to pi little r squared. So now let's just rank these for each. So my favorite thing to do here is just to create sort of multipliers once again for each of these. So if we already know our area, we're sort of good. So here we can just say that we know that resistance is equal to rho L over A. So this means resistance is proportional to L divided by A, because all of these are the same material, so I'm not even including that resistivity term. So here, R1 is equal to, the length is just going to be 1L, and the area is just A. So R1 has a resistance of 1, we'll call it. What about 2? Well, R2, I actually don't know what A is yet, so I can just say that A is going to be equal to, well, I halved the radius. So this area is going to be 1/2 squared, which is going to be 1/4. So if I do this one, right, because I halved the radius, so if you half the radius, you 1/2 square the area. So R2 is going to be, the length is still 1, but the area is 1/4. So it makes sense that this is going to be a much larger resistance than we got before, because it's the same length, but I quartered the area, so I restricted that. So we started with 1, now I have a resistance of 4. And now going through here, this one, I just doubled the area, so I can just say R3 is just going to be the length is 1, the area was doubled, because I doubled the area, not the radius. So you have a resistance of 1/2. Makes sense that this one is lower because of the same length, but I give it more area to work with. And then finally, here, our length is 2, and our area is 1. So our representative resistance would be 2. Which makes sense, once again, because I've just doubled the length. I've just doubled the length without changing the area, so I got my longer hallway. So our resistances are 1, 4, 1/2, and 2. So we can just rank them now. So the smallest resistance was the short wire with a big area, which makes sense, because you had a short wire, big area. Our next resistance was the average one. Average, normal length, normal area. Our next resistance was a longer wire, but the same area. So long wire, long wire, normal area. And then our greatest resistance was the normal length wire, but the smallest area because it was compressed by a factor of 4. So that's why R2 is the biggest. And if we actually did our representatives, this was 1/2, this was 1, this was 2, and this was 4. So that's my approach to ratio questions. It's really understanding the multipliers. So I usually say find the simplest case and call everything in the simple case 1, and then just do some multipliers and fractions along the way. You could totally have derived expressions, but that's more work than it's worth. All right, this is a fun one. So this actually really has us think about length and area. So the solid resistor shown below is a rectangular prism with a resistivity of 16 ohm centimeters. And we're going to calculate the resistance when current travels in all the directions. So first, we're going to send current through the x direction, which would be this way. We send current from left to right or right to left. Then we send current in the y direction, which would be sending current through the top of the block. And then we're going to send current into the block that way, because that will change who is L and what directions become involved in the area. So we know that in all of these cases, it's going to be resistance is equal to rho times L over A. So the resistivity is the same, but if we change the direction of current flow, we change what length to use and what area. So if we want the resistance in the x direction for current, we're going to use our resistivity, but take the length that it travels. The current travels in the x direction, so that means the area must be in the other two. So that's going to be how we solve this problem. You pick the length as the direction of current flow, and then you just multiply the other two dimensions to get the area. Because again, our length, if we're going in the x, is going to be this length, which is 1, and the area it flows through, would be this rectangle, which we can see is going to be 4 by 2. It's that other face. So we get 16. Our length is 1, and our area is 4 times 2. So we get 2 ohms in this direction, 16 over 2. All right, now for the y. So for the y, we can speed this up. We can speed this up now that we see the method. We take our length in the y direction and multiply by our area in the other two. Resistivity is 16 ohm centimeters. Well, the y direction, that's towards the top of the page. So the length we're using is going to be 4. And then for the area we're going to use, well, that's going to be the area in the xz plane, right? If the current is going this way up, this means our cross section is going to be this, which is a 1 by 2 rectangle. So that's 1 by 2. So we get 16 times 2, 32. And what about the z direction? Well, you know what it's going to be at this point. Yeah, it wants everything. Nope, laziness strikes again. Can't be lazy, have to write it out. Take the length in the z, take the area in the xy. So we know it's going to be 16 for our resistivity, multiplied by some length, and then we have some area. Okay, well, z direction, that's into the page. So current goes sort of this way, into the screen. So that means that the length we're going to use is 2, because into the screen would be this way. And then for the area, that's this. So that's going to be 4 by 1. So 16 over 4 is 4, times 2 is 8. And notice we actually could have ranked these without doing any calculations. So we see that the x direction is the least and the y direction is the most. Should make sense, because in the x direction, we have the shortest length and the biggest area. But in the y direction, we have the biggest length, but the smallest area. So it actually does make sense that x is the smallest, y is the largest, and z is intermediate. And then to conclude, we'll do a little best fit line. A group of students measured the resistivity of modeling clay, or they want to find the resistivity. That's a little typo. They form a cylindrical strip and use an ohm meter. You can guess what that does. Measures ohms to record the resistance R for different lengths X. The strip has a constant cross-sectional area of 10 to the minus 4th meters squared. So we're essentially taking one of these probes and we're scooting the other one sort of along the length of this strip, because it should make sense that the longer the strip is, the more resistance you get because you're forcing it through a longer hallway. So first thing before we graph is we want to actually figure out the relationship, because how do you know what to graph? Well, you got to come up with a relationship. So probably guess what equation it is. We start from resistance is resistivity times length divided by area. And in this specific problem, what's the length? Well, the length is just going to be this length x. So it's actually one of our variables. And the area is actually a constant. So we measured resistance in x. So actually, this is quite simple to linearize because there's no linearizing needed. It's linear. R, no transformation needed on R. So I put that in the box. Is equal to rho over A, resistivity over area is a constant, times X. So I put X in a box. So notice here we have, just for consistency, we're going to keep this as X. We're going to call you rho over A. I just like to match my colors like this. So what this does for us is, notice we can now write this as Y equals M times X. So if we graph resistance versus X, we can come up with a slope or y-intercept relationship. 99% of the time, it's the slope you're interested in. So we'll shrink this so I have the space. Which means that our slope is the number in front of the independent variable, which is rho over A. A is a constant, 10 to the minus 4. So this means that the resistivity is going to be area times slope. I always find it good practice to work out like the answer ahead of time, because then you just plug and chug it. All right, of course, we're not going to graph this. I mean, you can, but I'm going to do my first of many off-camera mining sessions and best fit this. So if we graphed it, we would get a pretty straight line. Notice here's our good practices for making a best fit line and getting all of our points. Label your axes with units. So I graphed X in meters. I scaled it linearly. I labeled my y-axis resistance in ohms with units, scaled it linearly. I plotted the points roughly correctly, and then I drew a best fit line trying to get roughly half the points above and below. Then we go to our mathematical savior, Desmos. We type in the data, and this is what it spit out. So why do we care? Well, we just came up with this fact that we said actually the slope of our line was equal to resistivity over area, which means that resistivity is equal to the slope times the area. Our slope was 3630. And we'll do the units here, why not? The slope was our rise, which was ohms, divided by our run, which was meters. And then area is 10 to the negative fourth meters squared. So that's pretty easy to multiply. We just got to scoot our decimal 4 over to the left. So this would be 1, 2, 3, 4. So we get 0.36 ohm meters, which is about what we get for Play-Doh when we do this lab in my class, which is why I picked this as the resistivity. So that's everything there. And also I should note that this is not the only linearization. There are some of you that I will call slope purists. I change which one I am depending on the year. That you only want the answer to be your slope, so you do some algebra ahead of time. So actually, if instead of graphing x, you graphed the quantity x divided by a, that would make your slope the answer to the question, and you'd just have to best fit, and you don't have to do anything else. But most people prefer to graph the simplest possible relationship that involves little transforming, and then you just do some math with your slope at the end. Both are totally valid. So if you disagree on how to linearize, as long as it's a straight line, it's probably right. You just have a difference relationship. So if you graph something else, maybe you don't get slope is rho over a. You get some other relationship. Totally valid. All right, that's our microscopic current and resistance.